Hey everybody. So what I want to do in this video is kind of introduce you to the idea of what a chi-squared test is. So just kind of give you a general overview of the three tests we're going to be doing chi-squared with and kind of how they work and give you a little bit of just kind of base understanding of what's going on. So this is just kind of an overview of all three tests, how it all works. And then in future videos, I'll break down and look at each of them individually and tell you actually how to do them. So the question we should be asking is, what exactly is chi-squared? It's not an x squared chi because it's a Greek letter there, chi-squared. So in short, essentially what chi-squared is going to allow us to do is it expands our capabilities of one proportion, two proportion z-tests. So we're going to be able to do a lot more than just doing a simple one proportion z-test or two proportion z-test. In some cases, it allows you to do multiple of these tests all at the same time. But instead of trying to do each of them individually over and over and over and over, it does it all at once. Now, why might that be helpful is, well, first off, it's a little bit more efficient than just running multiple one proportion z-tests over and over and over again. But additionally, you have to think about the ideas of type 1 and type 2 errors. Every single time you run a test, you have a chance of committing a type 1 and type 2 errors. So if you're doing a one proportion z-test, another one, another one, another one, that's a whole bunch of opportunities to commit a type 1 or a type 2 error. Where if you can kind of take all those tests and condense them into one big test, you're really kind of only reducing the risk of a type 1 or a type 2 error. So that's kind of why these come in. It's a lot more efficient and avoids mistakes like that. So first of the three tests that we're going to do is a chi-squared goodness of fit test. So essentially what these types of problems are going to look like is you're going to have basically one sample from one proportion, which is kind of what we've done before. And then you're going to have a categorical variable, except we're going to have two or more categories. In the past, when we did one proportion z-test, we only cared about success or failure. Were you going to prom or were you not going to prom? Whatever. Okay, so what this is going to do is it's going to expand it, and the categorical variable is much, much bigger. So we're going to have two or more categories. An easy way to think about it is think about an M&M bag. So I can get a sample, get a single M&M bag, and I can look at and count how many red M&Ms there are, blue, green, brown, whatever. Okay, so it expands the number of categories you can have. So what a goodness of fit test is going to do is going to check to see if a sample follows along a hypothesized distribution of a category. So going back to that M&M example, what that can mean is M&M may claim you're going to have this percentage of red M&Ms in a bag, this percentage of blue, green, and brown. Well, what I do is I go out and take a sample, which is getting a bag of M&Ms, and I just count up and I see, does the distribution of my bag of M&Ms follow what they claim is what you should get in every single bag? That's what a goodness of fit test. Very similar, but there are some differences there, is a chi-squared test for homogeneity. So what this is going to do is it's still going to have a categorical variable, but with two or more categories, so same as up above. The difference here is we're going to have more than one sample. So we're going to have samples from two or more populations. So we might be looking at a sample here, a sample here, a sample here, a sample here, and they all come from different populations with category variables across the top. So what it's going to do is it's going to compare the distribution across categories between two or more populations. So you could still be looking at categories, but instead of saying, does my sample match up with a hypothesized distribution, you're more going to check, does the distribution across the categories match from one sample to another, to another, to another, which is across many different populations. That could be a tad bit confusing. Here's a basic example for you. So I could do the categorical variable of TV show preference. Do you like watching shows, the news, cartoons, dramas, whatever, okay? That's my categorical variable. But I might check, what's your preference in the United States? So across that population, I might pull a sample, and across, say, Europe, and pull a sample from there. So I might be comparing, okay, what do Americans prefer as their TV show versus Europeans? So a chi-square test for homogeneity is just going to see, do those two populations match up or not? Okay, do their TV show preferences match up. And you can even expand it. So I could have one row is Europe, one row is the United States. I could check Japan, whoever, and we're just seeing, does the distribution, when you change the population, does the distribution of the categorical variable, does it stay the same? So that's a chi-square test for homogeneity. So goodness of fit is a sample versus a hypothesized distribution. Chi-square test for homogeneity is there is no hypothesized distribution. You're just seeing, does your distribution match up from population to population to population? And then our final test we're going to look at is a chi-squared test for independence, which oftentimes these two will look very, very similar when you do the procedures, but there are some key differences there. So back when we did probability, we actually had an opportunity to determine if two types of categorical variables are, in fact, independent. This is an actual test to allow us to see this. So you're going to have a categorical variable, and you can have multiple categories there, versus another categorical variable, and you can have multiple categories there as well. So the entire table comes from one population, where a chi-square test for homogeneity, this is a sample from one population, this is a different population, different population. You have multiple populations in homogeneity. Independence is a single population, and we're pulling a single sample. We're just categorizing people across two different types of categorical variables. So an example is I could look at your TV channel preference versus your political preference. So I could look at, are you Democrat, Republican, Green Party, Independent, whatever, versus what is your TV channel preference? Fox, NBC, CBS, ABC, whatever. So I'm pulling a single sample, and I would ask people, all right, what is your TV channel preference? And also, what is your political preference? And then kind of write down where you fall. So what this is going to do is we're going to see, is there an independence there? Is there an association is another word that we see. So does their TV channel preference in any way affect their political preference in my specific example? So those are our three types of tests. One other thing I want to just touch on in this intro video is what actually is the chi-squared test statistic. So this is going to be the equation we are using. Chi-squared equals the summation of observed counts minus expected counts squared and divided by the expected counts. We're going to take the summation of that. Those of you in AP Bio, this formula should be very, very, very similar. That's why covering chi-squared in AP classes or in AP Stat classes incredibly important to those who are also doing AP Bio. So that is our test statistic. The good news is this is given to you on the AP exam, and it is the same formula for all three tests, so it's not going to change as you go on. As far as the chi-square distribution, maybe I'll back it up one second. What this chi-square test statistic is going to do is it's going to measure the distance observed counts are from the expected counts. So we're going to see how far are things differing from what we expect to happen, okay? So what we're going to have is we're going to have a distribution which is going to have skew to the right, okay? So a number line across the bottom, you're always going to start with 0. So this would mean, hey, there's no difference between what we observed happening and what we expected happening. And then as we go out to the right, we're going to see, all right, how much of a difference is there from what we expect to happen versus what we observe to happen. So another thing with chi-squared is we're going to have degrees of freedom. We'll talk about that more when we talk about all three tests. The degrees of freedom does have an effect here. So here is in blue my chi-square distribution, just really roughly drawn there with a degrees of freedom of 2. If I increase my degrees of freedom to say 20, you're going to see this kind of stretches out a little bit more to the right. So more degrees of freedom, you're going to see less skew, bigger numbers are more likely. Okay. One last final fact I want to touch on here in this intro video, and this is a neat fact. It's not really tested on, but it's always something to have kind of in the back of your mind when you're doing chi-squared. The mean, the average of these distributions, the blue or the red here, the chi-squared mean is going to be equal to the degrees of freedom. So let's say if you had a degrees of freedom of 10, then the average of that chi-squared distribution would also be 10. So say we went out, we collected our sample, we got a chi-squared test statistic of 10.2. So before we even look at the p-value, I already know my test statistic is going to be very, very close to the center of the distribution. And when you're close to the center of the distribution, you know things aren't too crazy. So this is kind of a fun fact for you to kind of get some sort of context of what is going on there. So if your test statistic is anywhere close to the degrees of freedom that we calculate, you should already be thinking, we're pretty, everything's kind of okay. When your test statistic is extremely far away from your degrees of freedom, that's when you should be a little bit on edge and be like, well, what exactly is going to happen? And you might have some of those reject and null hypothesis and things like that. So that's just a general overview of the ChiSquare test statistic. Yes, we will have different distributions depending on the degrees of freedom, so very, very similar to T. And then we'll have, honestly, our 3 tests, which I'll break down each of these a little bit more individually as we work through them. So that's just kind of your rough intro on what exactly is chi-squared and what are we doing.